In this lecture, we talk about classification of surfaces. So any compact connected surface S is homeomorphic to a sphere or connected sum of n torus or connected sum of projective plane. Now surface means that locally it looks like a disk. So if a small bug is traveling on a sphere, locally it will look like a disk in R2. So our assumption is that the surface S can be triangulated. The references for this proof, there are three references. So the first book is A Basic Course in Algebraic Topology by Massey. The second is Topology of Surface by Kinsey, and this third is on the web, Geometry of Surfaces by Nigel Hitchen. You can Google all three of them out. Now before we begin, we have to describe what triangulation of a surface means. So it simply means that you have a surface like this. You can put triangles into it and triangulate it. So this is a triangulation. This is another surface. So the boundary of the surface is in white and there is a triangulation inside it. So when you put triangles, you have to adhere to some rules. So the first rule is any two triangles are identified along a single edge. So say that there are two triangles here, 1 and 2. They are identified along a single edge or at a single vertex. So notice this triangle and this triangle are identified at a single vertex or are disjoint. So again, for example, this triangle and this triangle are disjoint. So this is not a valid triangulation. If you have two triangles coming like this, this is not a valid triangulation. Again, this is not a valid triangulation. So this triangle and this triangle share a side, but the complete side is not shared. So you have a full single edge you need to have for triangulation. Again, you have say two triangles like this. This is one triangle, this is the other triangle, and they share two vertices, one vertex right here and another vertex right here. Again, this is not a triangulation. Now since we are talking about surfaces, locally they should look like disks. So say if you take a point here, then you take its neighborhood, this looks like this, half disk. So we don't want this. So we will glue all the edges. So say this edge, if it is glued with this edge, then this will become a full disk. So neighborhood of the point here, so say this point, some neighborhood is here and then the rest of the neighborhood is here. So locally it still looks like a disk. So you will not keep any edges hanging. So for example, if you just pick up R2, then R2 will not be a good example because we are going to talk about compact surfaces. So R2 is not compact. So if you put triangulation on it, you can have infinitely many triangles. So since we are talking about compact surfaces, the number of triangles you can put on surfaces are going to be finite. So the cover with triangles is going to be finite. So cover is finite. So when we are going to talk about surfaces, we are going to consider edge by edge. So say there are two edges. So there is an edge A and edge A. These two are to be identified. So we put A and put arrow. And if these two edges are under consideration, the other edges we just put as jagged lines. So these are other edges. These are other edges and they are just jagged lines. Now if both these A's point in the same direction, we call them opposing pairs. So these are opposing pairs. So again, you have two edges under consideration. Say this edge is B and this edge is B. So one is pointing in this direction, other is pointing in the opposite direction. This we will call as twisted pair. So now we will come to the proof of classification of surfaces and show that surfaces are either a sphere or connected sum of n torus or connected sum of projective planes. We now give the proof of the theorem. So the proof is going to be described algorithmically and pictorially. So the first step is to eliminate adjacent opposing pairs. So recall that for a sphere, you identify these two sides of the disk. So you have a disk and these two sides you identify. So in Massey's book, he describes this as a lady's purse. You zip it, it will be a sphere. If you unzip it, it is a disk. So if you have these adjacent opposing pairs, you can identify them like this. If all you have is just these adjacent opposing pairs and you encounter no problem, you keep identifying, what you will get is a sphere. In the end, you will get something like this, and this will give you a sphere, and you are done. So your compact connected surface in this case would be a sphere. So suppose somewhere you get stuck, you do not have any more adjacent opposing pairs. Then you go to step 2. In step 2, we just have one vertex which will remain. That is, you identify all the vertices and there will be only one vertex which is remaining. So that is, all vertices lie in the same equivalence class. Now suppose you have vertices lying in two different equivalence classes. So we want all the vertices to be in one equivalence class, and suppose vertices lie in two different equivalence classes. One is a blue vertex and another is a green vertex. So obviously there are two different edges coming into the blue vertex, because if they were the same edges like this, then you would have identified them in step 1. So since you are not identifying them in step 1, these must be two different edges. So if this is the case, for this edge B there will be another edge B, because we don't want hanging open disks. Otherwise you could take an open disk here and this will just be a half a disk. So you have to have another edge B like this. So in this case, we just cut like this. So you cut here, say you cut like this, you call this C, and then you take this B and you identify with this B. So this blue vertex will go right here. So you will get this like this. So in this blue vertex right here is gone here. So as you can see, edge A is coming into this blue vertex, edge A is coming in, tail of edge A is green, so this is green, and then C is going into tail, so C is going into tail. So now you can see that you have two green vertices. So there are two green vertices and there is one blue. But we started with two blue. One was here and second was here, and one green. Now we have two green and one blue. So you can keep on repeating this procedure until you just have one green vertex. So if you have vertices like this, you can keep decreasing it. You can just choose the vertex you like. So in our case, we say we like green vertex. So we keep increasing the green and keep decreasing the other vertices. So step 3 is to collect twisted pairs. So you have A and A like this, and then what you do is you make a cut here. So you make a cut like this, B. So this triangle is right here and this triangle is right here. Then we identify these two A's together. So this edge is identified with this edge. So let us put a red vertex here. So this red vertex will come here. So this triangle is going here. So this will invert itself. So this red is here. So B is going into the red vertex. So see, one B is going into another B. So notice that for RP2 we have this. You have a disk and you identify edges like this. So in sphere, both of the arrows are going in the same direction. Here they are going into each other. So if all you have after this is just these edges going into each other, you will get n RP2 right here. Otherwise you will get some other toroidal pairing. So the last step is step 4, in which you collect opposing pairs. So here we collected twisted pairs, and we could have possibly gotten a connected sum n RP2 if we did not encounter a problem. So the only problem which we will encounter is a torus. So this we haven't talked about as yet. So first thing, you notice that there are no twisted pairs, because if there were twisted pairs by step 3 you eliminated them. So only thing you have is opposing pairs. And notice that A would lie opposite to A like this, B would lie opposite to B like this. Because if both A and A are next to each other or in the same side, then you will have one extra vertex. So you wouldn't be able to identify all the edges with each other, and as a result you will have one extra vertex. So by step 2 there is only one vertex which is remaining. So you have A like this and B like this. So you can't put A here and then a A here and a B here then a B here, because then you will have one extra vertex if you identify this A with this A and B with B. So the only thing which is remaining is some figure like this, the A here and B here, the opposing pairs. So first thing you do is you make a cut like this. You make a cut right here. Say you call this C. So you keep this kind of rectangle up right here, and you take this B and you identify with this B. So take this portion and identify here. So once you do that, this bottom C edge comes right here and top part comes here. Now you forget about this edge B and you go to this diagram. So we have forgotten about B. That's pretty much it. Nothing else has been done. So once you're here, then you make another cut here. So now we will make another cut. Say we make a cut like this. Call this D. So first you keep this kind of rectangle right here. You have C, D right here and A right here. Then we identify this A with this side. So say you have some big vertex here. So that is this vertex. Comes right here, and then this A is going into this vertex. So A is going into this vertex, but then this D is also going into this vertex. So you're identifying this side A with this side A. So these two vertices are the same. D is going into it, so D is going into it. So that is pretty much it. And then you have these jagged edges. Now we are going to forget about A. So forget about A because you have glued it. What you get is this. Now this looks like a torus. You can see D, C, D, D. So this C is identified with this C, this D is identified with this D. You can see the directions are correct for torus. If all you get is just toruses like this, as we have seen connected sum of n torus, all you get is just torus like this, then you end up with NT2 and you're done. So the only problem you're going to get is that you get a torus and then you get this projective plane, but that is essentially not a problem, because we have seen that you will get something like this, a connected sum of projective plane with a torus, and this is just equal to like n torus. So this we have seen before. So if you have a projective plane and connected sum with torus, you will just get this nRP2 again. So now the classification of surfaces is all done. So you either get a sphere, which is just by step 1, you encounter no problem, you get a sphere. Step 3, if you encounter no problem, you get nRP2, and step 4, encounter no problem, you get RP2. If you encounter a problem, then RP2 is connected with the torus, and then that will still give you connected sum nRP2. So for example, this is 3RP2, and that is the proof.